Hey folks, today in my recitation I was asking students how many distinct sets of hydrogens there are in this molecule. This isn't a thought, it's just a crack in our whiteboard. And a lot of people were saying 6, and I believe there should be 7. So what was throwing a lot of people off is that the hydrogens on this carbon are actually diastereotopic. So here's a quick video, just a review of some stereochemistry stuff that you guys learned last semester, and then an explanation of diastereotopism.
We'll start with a simpler molecule, 3-pentanol. 1, 2, 3, 4, 5. Alcohol, 1, 2, 3, 3-pentanol. Okay, so with this molecule, these two hydrogens are going to be diastereotopic. And this might be a little confusing because if you try to see if this is an R or S enantiomer, it's not an enantiomer, right? These are two same substituents on this carbon, so it can't be chiral. I'll show it in a mirror really quick. You'll see that this is an achiral molecule, but these hydrogens are still going to be diastereotopic. Yep, so let's look at this. We have this molecule. Maybe this actually isn't super easy to see, but look, here, that's the same molecule, you know? So this is not chiral, but it doesn't have to be chiral to have diastereotopic hydrogens, because for something to be a diastereomer, it just has to have multiple stereocenters and not to be a mesomorph, right? So if we replace this hydrogen or this hydrogen back here, we're going to end up with diastereomers. So let's show this diastereotopicity, I don't know. But yeah, let's show it. So looking at this, we'll first replace this front carbon, this front hydrogen, the one on the same side as this alcohol, with an orange deuterium atom, okay? Deuterium is going to be larger, and when we do our Kohn-Engel prelog, if you guys remember that from determining the R or S configuration of a stereocenter, this is going to take precedence over a hydrogen. Okay, so let's quickly check what the configuration of this diastereomer would be. So we'll start here. We're going to start with this alcohol. We're going to put the smallest group, this hydrogen, in the back. This now has 4 different substituents: alcohol, hydrogen, ethyl, modified ethyl. So obviously this is going to be a stereocenter. We're going to go here. We're going to start on this alcohol. We're going to move to this next largest group, and all the way back around. So when we do that, we're going clockwise. That's going to be an R stereocenter. Now let's go to this one. Here, we're going to put our hydrogen in the back. This group with the alcohol on it is going to be our largest. This methyl is going to be our second largest, and this deuterium is going to be our third largest. So we're going to go here, here, back to this hydrogen, right? Whoop. That's going to be R as well. Now let's try switching this out for the other hydrogen. So now we're going to have the hydrogen that is anti-periplanar to this alcohol be replaced with the deuterium. So here, we see that the alcohol is going to have the same configuration. This is still going to be R. This group, this group, this group, this group. Clockwise, right? And now we're going to move to here. We're going to have to flip this molecule around because we have to have the smallest group in the back. So let's go. Let me see how I have to rotate this. Right, Okay, here we are. Here we have this carbon attached to the alcohol. It's going to be our biggest group. This methyl is our second largest. Deuterium, third largest. Hydrogen in the back. Okay, so when we do this, we're going to start here, go here, here, here. Here to the hydrogen. So this is going to be counterclockwise. This is going to be an S stereocenter. So let me put this back how we were looking at it before. As you can see, we went from RR to RS, meaning these are diastereomeric molecules, which means these hydrogens that we replaced to show that are diastereotopic hydrogens. Okay, so let's quickly compare that to N-pentane, right? This is N because it's a linear chain. Any hydrocarbon that starts with N is always going to be a linear chain, and it's pentane because 1, 2, 3, 4, 5. Okay, so let's replace this hydrogen with a deuterium. When we do that, we're going to see biggest group, second largest, third largest, hydrogen in the back. We do that, we're going to go clockwise. We're going to have R stereochemistry. We replace this back hydrogen instead, and we're going to have S stereochemistry, right? Here, 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 here. So this molecule and the molecule I just made are going to be enantiomers, which means that this hydrogen and this hydrogen that used to be there are enantiotopic hydrogens. One thing that is very important to know about organic chemistry is that chiral molecules, enantiomeric molecules, cannot be distinguished and cannot be seen by achiral molecules. There's actually a very cool, just a side note for any chem fans out there, there's a very cool mystery in chemistry on where chirality arose from. I suggest looking up origin of chirality in life if you're interested in that type of thing. But back to organic 2. As we just saw, these two hydrogens are going to be enantiotopic. And because we do, sorry, my phone is at a little better. Because we do achiral NMR, we're not using a chiral solvent. We're just not using chiral solvent. We're not using anything chiral. These two hydrogens are going to be indistinguishable, right? So these would be considered the same hydrogen. It would have an integration of 2. Okay, so in reality, these hydrogens, although they're diastereotopic, are going to look exactly the same by NMR. Theoretically, this hydrogen is being split by one distinct hydrogen, and then 2, but these are the same. So this should be a doublet of doublets of a triplet, right? Because 1, 1, 2. But all of those splits are going to be so small that this hydrogen is going to show up at the same shift as this guy, and it's probably just going to be split as a quartet from these 3 neighboring hydrogens. Okay, so, but let's imagine that we do care about this, and there are molecules where you will see differences in diastereotopic hydrogens. So let's say this is, instead of an oxygen, it's the most electronegative thing you've ever heard of, and it is evil, and it's sitting right here, and it's going to be stealing all of the electron density that is left sitting on this hydrogen and just pulling it through something called a field effect, a through space effect, and it's going to just rob this poor hydrogen of all of its electron density, really de-shielding it and pushing it a lot further than this hydrogen. So let's motivate how that could happen, right? Let's look down this bond, and we'll see we have 3 conformations. This bond can, 3 staggered conformations, I should say, where this bond can show up. We have this first one, pretty good. It's got this carbon just next to this oxygen. That's acceptable. We can rotate it 60 degrees. This is looking worse, right? We have this methyl group gauche to another carbon chain. That's not good, we don't want to see that. And then we'll shift it 120 degrees, and we'll see that's even worse than before. We have a methyl group clashing with this and clashing with this oxygen. That's small, but not as small as a hydrogen, So we're going to shift it back here. This is the best conformation that we can be in. If this was something super duper electronegative and we did a NMR at, let's say, like negative 87 degrees Celsius, something super cold, that's going to start hindering this bond rotation and going to lock this molecule in its lowest energy conformation, which would be this, if we look at this little Newman diagram type picture that we've just done. So in that scenario, not a real scenario, but in that scenario, that's where we would see different shifts for these 2 hydrogens. And that's why it's good to know about diastereotopicity, we'll call it. Cool. So this is a molecular model of that first molecule we were looking at, where we have this kind of heptane body with these two terminal methyls on this carbon 3 and 5, right? So a lot of people were asking, right, if these guys are going to be diastereotopic, right, for the same reasons we just discussed, why aren't, I really hope you guys can see this, why aren't these, this methyl group, why isn't it going to have the same issue, right? Like, why aren't these hydrogens going to also be diastereotopic? So, I mean, the best way to do it is we'll just redo our test. So let's swap out this hydrogen for a deuterium. Okay, so here, now we have this molecule. You can just instantly tell that we're not going to be able to find an RS configuration for this carbon because it still has two of the same substituents. And the reason that's important is because, let's say instead of this one being swapped out, we swap out this hydrogen down here. When we do that, looks like we have a different molecule until we just rotate this 60 degrees. There's free rotation around that bond, and boom, this is the same molecule that we just made before. If we put the deuterium here, rotate this way, we have the same thing. Deuterium here, rotate this way, same thing, right? So that's why these hydrogens on this terminal methyl group are not going to be diastereotopic, even though they're still 2 carbons away from this chiral center that we have, okay? And yeah, just to really make sure we have this, I'll show this diastereotopic thing on this large molecule, but it's going to be the same exact thing that we just looked at. So here, this molecule is going to be in its, let's see, yeah, going here, 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 here. It's going to be in its S form. Replace that with this. Now this is going to be an R stereocenter, and this is this carbon for both of those molecules, where this is R and S, is going to be R, right? So we have RS and we have RR. Yeah, we have RS and we have RR. So these are clearly diastereomers, right? So diastereotopic hydrogens, we don't have to have a chiral NMR to see that those are different. Cool.